Hi there, my name is Giuseppe. I'm lead machine learning programmer at Milestone, and I'm going to talk about reinforcement learning and how we are using it to produce the AI of our racing games. We'll begin introducing reinforcement learning. Then I'll show you some problems we had to face during the development. Then I'll talk about our reinforcement learning framework. And finally, I'll show you some results. If you use reinforcement learning, you do not program your AI. You don't tell it what to do step by step. You rather design it by goals. But first, some little glossary. The AI is called agent, and the game is called environment. In our case, the agent is a neural network, which is a tricky mathematical expression, the computational graph, with many inputs and many outputs. Inputs are called observations, and outputs are called actions. The computational graph depends on many parameters, called weights. Weights are the result of training. We train to find the weights that maximize the rewards. What's the rewards? A reward is a score, a number we assign step by step to the agent to tell how good it was in its performance. The training is composed by episode. What's an episode? An episode is a short race with a random number of competitors. Every competitor is a clone of the same agent. After the episode, we update the weights to maximize the rewards, and then the loop repeats for thousands of times until we get a training agent. What the agent sees? We show some samples of the track borders for short period trajectory planning, and for long period trajectory planning, we show some samples of the curvature. We also cast some rays to detect obstacles and show the distance of intersection or the time of impact. We also show some useful physical quantities like velocity, lean, and the grip of the wheels. Now let's go to the joypad of the agent. The domain of actions is quantized. Actually, the output of the network is a probability for every possible action value. The numbers you see are just an example. As you can see, there is a map to 1. This for every axis. Now, you got the probability. You have to transform them to a single action value. We have two strategies to do that. One for the game and one for the training. In the game, we compute the average of the action values weighted by the probabilities. So it's just a dot product between action values and probabilities. This gives a very smooth action value, which is very nice for the game. During the training, we do something different. We just pick an action value randomly, using the probabilities as distribution. Now, when we start the training, we initialize weights randomly. When you do this, usually you get a flat distribution. That is, all probabilities are the same. In the opposite, a trained agent, an expert agent, has one spikes on the probability. That means all probabilities are 0, but 1, which is full. This is a very nice self-balancing trade-off during the training between exploration of the environment and exploitation of your knowledge. Often people ask why we restart a training from scratch when there is even a small change in the environment. This is the reason. An expert agent, a trained agent, does not explore. It's too confident and does not adapt. You may have been a programmer for something like 25 years, like me, and be expert on classic computing, but you may feel uncomfortable approaching to quantum computing. Well, I admit I don't get quantum computing. It's too strange for me. Maybe my son will get quantum computing. Why? Because he's a clean mind. He's an entropic mind. He did not waste his time with, I don't know, template metaprogramming yet. He will waste his time with something totally different, maybe quantum template metaprogramming. The point is, an expert agent does not adapt to a new environment. You must be a newborn agent to adapt. Now let's go to what agents live for. We have negative rewards for nasty agents. When they go out of the track, they collide, or they just fall. Of course, we have positive rewards, for example, for overtaking. But the overtake reward is not that important. The important reward is the catch-up. Catch-up is the reason why our AI is actually working. What's the catch-up? It's just a reward proportional to the time gap between me and the one in front of me, or much better, between me and the average of the others. So with catch-up, I'm racing against myself. If I do by exploration better than my average, I have a positive reward. If I do worse than usual, I get a negative reward. And this brings us to the training algorithm. We are using Actor Critic. With Actor Critic, you have two neural networks. One is the critic, and the other is the actor. The actor is the actual driver. Its outputs are the actions. The critic tries to predict the results, the rewards of the actor. Now, you may think to the critic like the coach of an high jumper, and which places the bar based on what the jumper usually does, and to the actor as the jumper, which must jump over the bar. After every episode, we update the weights of the critic to make his prediction closer to the results of the actor, and we update the weights of the actor to do a positive reinforcement on the actions which gave better results than the prediction of the critic. In the opposite, we do negative reinforcement on the actions that gave a result worse than the prediction of the critic. Now, you may use two neural networks for Actor Critic, or you may use one single neural network, which plays both roles of actor and critic. In this case, they share the same weights. They are the same thing, but they get updated independently, so they don't know. It's just like a dissociative identity disorder. But this Tyler-Durden neural networks allows us to train just one network. Finally, the loss. The loss is the function that we try to minimize when we update the weights. And of course, it depends on the performance of the actor and on the prediction of the critic. When we update weights, we just push them a little in the direction that minimizes the loss. To do this, we assign a momentum to the weights. Why? Because if you have a momentum, you can jump over holes in the loss function. You may pass over some trenches. This is like Newtonian dynamics versus Aristotelian dynamics. If you have some kinetic energy, you may jump over the noise and some little holes. And now we are done with how it works. Now we go to the how it doesn't work. I said that a trained agent has one spike on a single action value. This is not always true. Sometimes you get an agent, a trained agent, with two spikes on the probabilities, separated by a please don't zero probability region. So there is a fork, you can go left, you can go right, just don't go straight. In this case, weighted average gives you the worst answer ever. There are many ways to fix this. For example, you may use maximum probability as action selection. That means just picking the action value with the highest probability. Or you can mix two different action selection strategies to make a Frankenstein action selection. Anyway, this is not a difficult problem. What is a difficult problem is credit assignment. What's credit assignment? Let's suppose I eat a candy, I set fire on my room, and I sit on a chair, and then I get pain. Which action was responsible for the pain? Well, I don't know, but I want to know because I have to do negative reinforcement on the bad action. The point is that usually the effect, the reward in this case, and the cause, the action, are separated in time. So what we do is just reinforcing all past actions depending on the distance from the reward in time. This is a very, very brute force approach. It works by statistics. We make good behavior emerge by big numbers. That is tons of episodes. I believe this is the biggest open problem in reinforcement learning. We are trying to modulate the reinforcement with the derivative of the critic with respect to observations and actions, but it's still an open problem. Now let's talk about greediness. If you are an employee and your employer asks you results every hour, your long-term results will be very bad. Why? Because you cannot afford a strategy. What's a strategy? Strategy means sacrificing short-term results for better long-term results. Now, for example, the ketchup. The ketchup is assigned on checkpoints along the track. If checkpoints are too much close to each other, agents will be very greedy. In the opposite, if they are too far each other, you may have a newborn agent that will not discover the reward for the first time at all. So you just have to tune this kind of trade-offs. Now you design the rewards, you set up, prepare the environment, but you don't get what you expected. This may happen for several reasons. The worst one is when doing something strange or doing what you expected has no consequences on the racing performance. If you have this, probably the problem is in the game. It's very hard to fix this. Now, when we were beginning, we were starting episode from the starting grid. Anyway, we often had agents exiting in the first turn. exiting from the track. This happened because agent would learn to accelerate at the beginning of the episode, and then they would see the turn when they are very fast. So doing the turn in this case would require a big sequence of correct actions, which is very unlikely to get by random exploration. The solution is starting episodes in random points of the track with procedural starting grids. So the agent will see turns and straights at the same time. Now, about the termination. Do not terminate episodes after a fall or an exiting from the track. Do not make termination depends on what the agent does, because otherwise you will get sometimes agent which want to terminate the episode early. If you give a way out from the episode, maybe sooner or later your agents will use it. So often we had agents suiciding even at the beginning of the episode. The solution was to remove the way out from the episode. Just use a timer to terminate the episode, and use a random duration, because otherwise with a fixed duration agent will be maybe very greedy at the end of the episode. So you in general should randomize everything you can. Now let's talk a little about our reinforcement learning framework. We specify the computational graph with plain C++ code or with a custom scripting language we have created. The computational graph is simplified, is optimized, and then is converted to C code. Then the C code is compiled with a plain C compiler in a DLL, and the DLL is loaded into the process. So we do the evolution of the network and the update of the weights with a single very fast, very quick call. About performance, be very careful about locality of memory access. It's very important. For the training, we use a custom game mode with a custom game loop in which we update only the physics and the AI. We don't even do collision detection. We just detect collisions and assign rewards. We don't do collision response. This is a very quick way of simulating the game, but it's a very bad when you want to understand what's happening. So we have a telemetry tool to understand and analyze what's happening in the training. It's our Sauron eye. When we start a training, we assign to the agent a configuration in which we specify observations, rewards, actions, and also the structure of the episodes. During the development and the production, we keep a default configuration, which is the best we have until now. And if we have some experiment which proves to be an improvement, we update it. Always try one change at a time. Don't mix changes. Otherwise, you will not understand if the change is positive or negative. We also have several random name generators for the agents, which is one of the funnest things of reinforcement learning. We work together with designers a lot. The designers is very important in reinforcement learning. He acts like a psychologist, trying to understand the reasons behind the behavior of agents, because you cannot debug agents, you can debug neural networks, they are too complex, so you just have to understand them. We as programmers, we are more like neurologists. We deal with Kunans, amnesia, low-level stuff, but most of the analysis is done by designers. Sometimes you see agents doing something, some strange trajectory, which you would not expect, which is not the one that you see in reality. When this happens, it's very hard to tell if it's a flaw, a defect of the training, or which is just is better in your game. This is a very, very hard question, and there is no systematic way to answer it. And often people has different diverging opinions. Now, let's see the results. I hope this is not a suiciding agent. This is MotoGP 20. In a few months, Ride 4 is coming, so you want probably to buy it. Thank you very much.